Hello everyone. Good morning, good afternoon, good evening, wherever you are in the world. I'm Zeb Bhatti and welcome to the Trust Era. Today's video is going to be on digital twins, which is a very important component of the Metaverse. So what are digital twins? Well, digital twins refers to virtual replicas in form of 3D digital models of humans and other life forms, physical objects, systems, or processes in the real world that also exist as a counterpart in the metaverse. Digital twins are created to simulate real-world entities using data from real-world entities, sensors, and other sources, and they use artificial intelligence algorithms for interaction with these entities. Digital twins of humans or other life forms are in form of 3D avatars, like in the 2009 Hollywood movie Avatar, if you've seen it. Digital twins are used in various industries, such as manufacturing, distribution, construction, tourism, aerospace, automotive, energy, even education and infrastructure management, many others. They're virtually everywhere. Digital twins are essentially driving the future of engineering. For example, by creating a digital twin of an engine, an aerospace engine, engineers and decision makers are able to test and analyze the impact of changes, upgrades, maintenance, etc. in a controlled environment. This reduces costs and associated risks, and also it makes it very easy to implement changes in the real world. At the simplest level, digital twins are realistic virtual representations of a physical entity. This entity can be anything from a human, animal, automobile, train, windmill, or anything. So here's a conceptual representation of digital twin technology and its relation with the counterpart physical asset. You can see that on one side you have the physical asset, and it has sensors like IoT sensors and all kinds of other sensors. Also, there's machine learning involved and artificial intelligence algorithms. And then you have the realistic 3D model and computer vision and artificial intelligence software interacting with it through the very high-speed networks with sophisticated high-speed edge technologies, cloud computing, and big data. And the information is flowing back and forth between the physical asset and the digital twin in real time. Some of the key benefits of using digital twins in enterprises are that they enable better informed decisions. They improve efficiency and streamline operations by providing insights into how their assets function in real-life scenarios. Some examples are, for example, predictive maintenance. By monitoring the performance of physical assets in real time and analyzing their historical data, digital twins can predict when maintenance or repairs are required. And this minimizes downtime and obviously reduces operational costs. For design optimization, digital twins are very valuable. They can be used to simulate and test various design alternatives before going into the manufacturing process, enabling engineers to optimize designs for efficiency, reliability, and performance. This all happens before implementing them in the real physical world. Performance monitoring is another area. By analyzing the real data collected from sensors and other sources, Digital twins can monitor the performance of assets. This helps identify inefficiencies and areas of improvement. They're being used and are extremely valuable in training and simulation. Digital twins can be used to train employees in various tasks or scenarios, providing a safe and cost-effective alternative to real-world training exercises. And of course, in decision support, by simulating the impact of different decisions on an asset's performance, digital twins can help organizations make better informed decisions, reducing risks and improving the overall efficiency. There are companies today that are bringing smart city planning and also scale up to deployment of digital twins. They recreate a complete city and organization down to the finest detail in 3D, allowing their citizens to explore, propose changes, and offer comments. This is already in use in several cities across the world, and it's helping them overcome disruptions from pandemics. It's helping them reduce cost and improve efficiency and better service to provide better service to the citizens. So as you can see, the benefits offered by digital twin technology are enormous and across the industry, across industries. There are countless simulations that are done that reduce time and costs and even save lives. And overall, this is where the future of Metaverse or the way we carry on day-to-day life is going to be. Each human is going to have a counterpart living in a virtual world. In a metaverse, digital twins serve as a virtual replica of, for example, real buildings, transport, real buses, trains, people, trees, animals, plants. There's even projects where digital twins exist for trees and are monitoring the growth of a tree and its output, if it's a fruit tree or something valuable like that. And almost everything that we need, that we can see and touch in our world, in the real world. And this all happens using AI sensors, cameras, computer vision, and the digital replica of the real world entities kept current with a constant flow of an influx of data back and forth between the real entity and the digital twin using high-speed networks and AI. By simulating the physical state and even the biological state and behavior of real-world entity based on input data, digital twin technology is definitely going to revolutionize our industry world and practically transforming all sectors of the manufacturing industry, construction, transport, healthcare, education, everything, smart cities, anything we see around us. It is important to note that in a metaverse, 3D objects can exist that are not necessarily replicas of the real-world objects, but are virtual creations of developers and users to whatever their imagination and the available technology permits them. This is evident from the many realistic and engaging 3D virtual reality and augmented massive games that are available. These are massive online games, and that they don't have, many of them don't have any physical counterpart, and are just an approximation of physical objects. And these are meant for entertainment and training and exercises and so forth. So now let's get into a real-world example of a digital twin, so that you understand its impact. We'll take an example of a dairy farm, and we'll call it a digital twin dairy farm. The entire farm has a virtual 3D model. All livestock and facilities are an exact replica in real form of 3D digital models. that actually are a counterpart to the real physical objects on the farm. The application of digital twins within the livestock farming sector, for example, can be used to improve large-scale precision livestock farming practices, machinery and equipment usage, and also better health and well-being of farm animals. The mental and emotional states of animals can be monitored using recognition technology that examines facial features such as ear postures and eye white regions and other stuff that tells the health of the emotional and physical health of the livestock. When used with modeling, simulation, and augmented reality technologies, digital twins can help dairy farmers to build more energy-efficient housing structures, predict heat cycles for breeding, discourage negative behavior of livestock, and potentially much more. Digital twin technology promises to help farmers better predict and discourage negative animal behavior, track and prevent disease from spreading or becoming serious, and improve in energy efficiency, as well as animal comfort and well-being in housing structures, and reduce the overall costs of livestock losses in breeding operations. Digital twins promise to revolutionize potentially all aspects of livestock farming if it's applied there. In the farm world, within the Metaverse, for example, by combining big data, real-time information from individual farm sensors on equipment, livestock, and also using AI algorithms, farmers can obtain a precise picture of what is occurring with their livestock, housing structures, and equipment and other assets. So here's an illustration that explains at a very high level the digital twin or the digital virtual dairy. One simple use case is the optimization of feed intake for cow, among scores of other use cases. The physical asset has sensors, as you can see, and then there's a counterpart of the physical asset in form of a 3D model that the end user has on their computer, and they're connected via high-speed internet and using massive storage and cloud computing and machine learning and also sophisticated AI algorithms to interact and monitor the real-world asset. So how are digital twins implemented? First, a realistic 3D model must be created to the exact specifications as the real object, whatever the real object is, whether it's human, animal, or machine. Then, to realistically represent a physical asset and mirror its behavior, the digital twin needs to obtain real-time feedback on how the physical or the biological asset is interacting with its environment. This means workload and other variables have to be accounted for. This requires different sensors that can send and receive specific forms of data via the internet or some other privately secured network. Next, we need the digital twin to be able to receive, store, and process the large volumes of data in real time. This requires a significant amount of computing, storage, and data processing capacity, something that is now available and getting better due to massive advances in data centers, big data, cloud computing, blockchain, and AI. So once that's done, the digital twin must be able to make sense of the large volumes of continuously transmitted data, all that is coming in real time. Here, AI algorithms are used to filter and discern between useful and non-useful information. It also means using AI algorithms to suggest recommendations, make improvements, and take actions that help optimize the asset utilization and the bandwidth and so forth. Next, the digital twin must be able to learn about different cause and effect scenarios over time and be able to apply the learnings to improve the performance of the physical asset. This involves running several alternative scenarios, test cases, and what-if simulations. This requires that AI and ML, machine learning algorithms, must be trained under specific circumstances to learn, experiment, and evolve and arrive at the best possible course of action. Finally, all this must be readily available to users via interactive and preferably an immersive user interface. In addition to these, there are several interconnections and there's information flowing in real time, and asset states and the object states have to be managed, and they exist between these three entities. Most of them will vary from the Metaverse project and purpose, so technologies used will also vary accordingly. Artificial intelligence plays the largest role in collecting and utilizing this data in real time to feed the digital twins and take corrective action or responsive actions. So in this illustration, you can see the flow of information between the physical object and the digital twin and all the elements of machine learning that are involved in the middle. So at the bottom, you see there's a human interface, and you have physical asset and sensors at the top. And from the top down, we see the sensors transmit data into the network, and the network stores and forwards the data and this, to the algorithms and all the computer software, and also going through the machine learning and AI processes for training the data or utilizing existing trained data, and the simulations and all these things are involved. And then eventually the user interface has to be friendly, which lets the user interact with the digital twin as if they're in real time. And the users can then send appropriate actions and instructions upstream to either change the state of the physical asset or monitor it or give it any feedback. So there's also always a constant feedback loop and connection between the user, the digital twin user, and the physical asset and the sensors on the asset. So unlike traditional 3D computer models, the effective use of digital twin does not require an understanding of all the technical details behind its creation. Instead, users focus efforts on learning about how the digital twin behaves under specific conditions. This is much like they would do with any object asset in the real world, with almost instant feedback. This is one of the main differences between traditional and computer vision models. A digital twin can potentially capture any data for which a sensor exists, and as the situation arises and reacts, and it interacts with the model as if in the real world. Computer vision is very much in use here, and it's a field of in AI, entangled with AI, and it enables computers to derive information from images captured and also videos taken and other inputs, and uses AI now to facilitate the process. There are many key terms that you should be familiar with in digital twins, which are the key requirements also. We have obviously the physical environment. This is the environment where the physical asset exists. Its location is most often remote and not easily accessible. And then you have a virtual simulation. This is the environment where the virtual digital twin exists, and this is very easily accessible through digital technology. Sensory states, it's a term you have to be familiar with. This is the different possible states representing changes in the physical asset. The changes in state, switching between various states in the physical asset or digital twin. A simple example is whether the door is open or closed, what is the temperature, and etc. Twinning, this is the synchronization of states between the physical asset and digital twin. And it also associated with twinning rate, the rate at which this synchronization occurs. This has to be as close to as possible in real time. And system processes, these are the various processes that cause changes, state changes to the asset or digital twin. So the interactions, complexity and frequency depends on the nature of the interactions required. The use of technology and input-output devices are also determined by the complexity and sophistication of the budget and also the feasibility of the interactions that is desired. The entities that are there, you have the individual. It must be a specific thing and identifiable. So, if, for example, if it's a cow, it has to be a specific cow with a name given to it. For example, Daisy the cow, rather than just a generic cow. Near real time, this means that the digital twin should be always on, available for as long as its real world counterpart exists. It must be data informed. It must be updated via digital measurements of the real world thing. Temperature sensors, speed meters, soil moisture meters, cameras, observation through other means, satellite observations, and so forth. So these are all the different types of sensors that are there to make sure that the digital twin is data informed. It must be realistic. Digital twin must be sufficiently realistic and a surrogate for the real world thing. And of course, actionable information from the real world digital twin, real world must have the potential to lead to some action. Here are some real world examples of digital twins usage in various industries. So, for example, the digital twin of a turbojet engine. All the operating sensors on the actual engine are synchronized with the digital twin counterpart. This way engineers can monitor and track the performance of the engine from a remote control room or a lab. In fact, because this is a digital twin, a copy can also exist in manufacturers' engineering facility and anywhere else that's desired. But all the copies are actually exact replicas and it's synchronization with the real asset. This is an example of a digital twin in a manufacturing plant. All operating sensors in the actual plant are synchronized with the digital twin. The engineers can monitor and track the performance of the machines from a remote control room or lab. A digital twin can have multiple copies, all tethered to each other, and also the real asset. This is another example of a digital twin of a warehouse and distribution center. All the operating sensors of the actual warehouse and plant are synchronized with the digital twin. This includes copies of replicas of the actual transport trucks and machinery, cranes, so forth. The managers, suppliers, production centers, shipping and receiving, accounting, finance, and all departments can view and interact with the digital twin of the warehouse operations in real time. This is another example. This is a digital twin of an entire city. In the near future, entire cities, along with their infrastructure of roads, bridges, sewerage, drainage, electrical, gas, buildings, sensitive locations, parks, malls, they'll all be digitized and exist in a 3D virtual world as digital twins. City centers and staff will be monitoring the entire city from a control room. IoT devices and other real-time sensors connected to high-speed edge networks will be very crucial for linking these physical assets to their counterparts. Now, humans are also creating digital twins so that they can be present in multiple places or be present in locations where they would normally not be able to go. Here's a real-world example of Ariana Grande Botera. She's an American singer, and she did a Rift Tour event. It was a virtual concert that took place 5 times live within the game Fortnite. Her digital twin was performing. She was physically not there. You'll see digital twins of museums. For example, artists can place their digital twin replicas of real paintings and have walkthroughs and events and so forth. In the transportation sector, we are already on the brink of being able to create digital twins for our highways and roadways. By collecting real-time data, we can create virtual copies of physical roads and systems. The benefits of this are countless, of course. Understanding exactly what is happening on the roads in real time has been the goal for the transportation departments and other agencies since the creation of road maintenance. Imagine Google Maps Street View updating in real time as objects move and change on it continuously. The power to see the change as it happens and have a ground level perspective from anywhere in the world will drive efficiency and scale that has never been seen before in our economy. AI algorithms and photogrammetry, which means photogrammetry is the technology for creating 3D models using photographs from all views and angles of objects, buildings, people, and so forth. This can automate roadway analysis. Currently, on-site road inspections are done manually, costing time and money and even loss of life many times. So rather than sending employees out to scan roadways and infrastructure for potential maintenance problems, AI can do this for us, allowing for more time to actually fix those maintenance issues. For example, if a large piece of debris were to obstruct a roadway and cause drivers to swerve out of the way to avoid it, a digital twin could notify engineers of the location, size, and consequences of the item on the road. This would allow for quicker and more efficient clearing of the debris and actually improving traffic flow and also preventing accidents. Digital twin technology is set to make organizations look dramatically different in coming decades. We envision a world where the lines between physical and digital environments will be blurred. Every asset, process, or person within and related to an enterprise will be replicated virtually and connected in real time. As a result, nearly every aspect of our work can take place solely digitally, or at least before it does so physically. Immersive experiences enabled by augmented reality and virtual reality will allow employees to gain real-world product design experience and training from their desks as they manipulate 3D digital replicas of equipment and also processes. As the technology of digital twin advances, more and more people will no longer need to go to offices or travel for work or travel to work or go grocery shopping or really go anywhere for that matter. There's obviously social implications for that, but we'll not get into that. We're just strictly focusing on the technology of course, staying indoors and not socializing has its negative impacts. So that's something that we have to address as well. So now a simple, the morning compute will be a thing of the past. People can jump onto virtual meetings to collaborate with other people from all over the world. And we'll be able to order groceries that will be delivered by self-driving vehicles. People will only use transportation when they want to, for leisure, not when they need to. So there'll be less reliance on fossil fuels and energy consumption. So overall, there's the positive side of making the environment and the planet a lot more greener. So life, as we know, is destined to change forever with the Metaverse and the technology.
And this is why blockchain disruption is something to take note of, and blockchain is disrupting the existing